So in this video, I will give you what's the definition, the real definition of the curl of a vector field. And using that definition, you can arrive at the expression nabla cross f, although I will not do this derivation because that derivation is in the optional PDF of further materials, okay? But I am going to give you the actual definition of the curl. So the curl of f is a vector, and the definition of the curl involves calculating the curl of f in a given direction, okay? So the definition of the curl of f in the direction given by n hat, so I can write curl of f dot n hat, okay? That will be the component of the curl in the direction n hat, okay? So that is defined once again as a limit. So it's the limit when the area goes to 0 of the following thing. If you have a vector field, let's say you have a vector field f, which looks something like this. Okay, looks something like this. And you want to calculate the curl at some point here. So what you do is you consider an area around this point which is perpendicular to the n hat direction. Let's assume that the n hat direction is out of the paper. Okay, so now I define an area which is defined in the paper. So I define, for example, this area here, a potato area here. So this will be my area A. Okay, and this area A is an area perpendicular to n hat. Why is it perpendicular to n hat? Because I want to calculate the curl of f at this point in the n hat direction. So I want to calculate the curl of the curl of f out of the paper. What's the component of the curl pointing out of the paper? So I define this area, and this leaves me with this contour or this curve that surrounds the area. Okay, and I call this the curve C. And I define the direction of this curve as following the right-hand rule, such that I end up calculating such that my thumb points in the direction of n hat, and the direction of my fingers is the direction of this curve. Okay, so using the right-hand rule. So I define the direction of C, of this curve C, surrounding this area A. And now I do the limit when the area goes to 0 of the circulation of the vector field f in this curve. And you remember that the circulation is written as the line integral of f dot product differential displacement dr, yeah, divided by the area. Okay, so I calculate the circulation, I divide it by the area, and I do that in the limit in which the area is made smaller and smaller until the area is an infinitesimally small area, and that will give me the curl of the field at that point. So then it makes sense that the curl tells you about the rotation, right? Because if you imagine trying to calculate the circulation around this circle, for example, so here the path is pointing in this direction. So clearly in this section here, this top section, the vector field f, which is these arrows drawn here, they are pointing opposite to the path, right? So we are moving anti-clockwise, but f is pointing to the right. So we will have a negative contribution to the circulation. While here on the bottom side, the path dr, so let me draw dr. This would be dr, yeah? dr. So in this bottom section, the vector field f, which are now these green arrows here, they are pointing more or less in the same direction as dr. So when you do the dot product, you will get a positive number. Therefore, when you calculate the circulation, you will get a negative number here and a positive number here. But since the field is stronger on the top than it is on the bottom, this means that the negative contribution to the integral will be bigger than the positive contribution to the integral down here. And therefore, the net circulation will be negative. And this will mean that the curl has a negative set component. Okay? So this makes perfect sense in all of these different cases, yeah? Including this case where the field is stronger on the top than on the bottom, which will mean that the total contribution to the circulation will be net positive. Or this case where the field is stronger on the right and weaker on the left, but if you add up the circulation, it all exactly cancels out. So this region of negative contribution will exactly cancel out with this region of positive contribution, and the same here with this. So the net circulation would be 0, and this would correspond to a curl of 0. Okay, so you can see how the definition of the curl does imply this kind of rotation around the point, and it comes from calculating the circulation of the field. Now, from this definition of the curl, you can derive the calculation, the nabla cross F calculation. And this is done in the additional notes. And just as a quick spoiler, this is how the derivation looks like. You have to consider a differential area whose side lengths are dx and dy. Then you need to find the vector field F at different points by doing a Taylor expansion. Okay, so first order Taylor expansion. And then you calculate the circulation by doing the sum of these 4 little paths. And by calculating that circulation and then dividing by the area dx times dy, you end up with the equation for the curl given by this. Okay, if you are interested in that derivation, it's written on my additional notes in the chapter 5.2. Okay, but at least now I feel a bit better that it's not that I simply gave you the equation and that's it. Now I feel better that I gave you the definition. So how is the curl and the divergence defined? Also, it's quite nice to notice how, after having learned in the multiple integration chapter, you learned about the flux and you learned about the circulation. So now it turns out that the divergence and the curl are related to the flux and the circulation, but it's like instead of doing it on a big area or a big surface, you are doing it on a single point. It's quite an amazing thing to think about. I encourage you to think about these things because it's always really nice. Okay, so that's the divergence related to the flux, and the curl is related to the circulation of a field, but locally at each single point, in the limit when the volume goes to 0 or the area goes to 0. Thank you very much for watching, and see you in the next video.